The purpose of this video is to introduce you to mass spectrometry. The good news is that you don't really need to know how mass spectrometry works. However, I'm going to give you a really simple and very brief introduction. What happens inside a mass spectrometer is you vaporise your sample. So here we've got some ethanol. Let's imagine it's been vaporised and turned into ethanol gas. What you do is you bombard your sample with high energy electrons. As that high energy electron hits a molecule, one of two things can happen. The first, and I would argue perhaps the most important, is it can knock an electron out of the molecule. So a high energy electron hits the molecule and bounces off, but in the process another electron is knocked out of the molecule, which results in the molecule becoming a positive ion. The MR of that molecule and the MR of that molecular ion will be the same. And that's really important. We'll talk about that in a moment. The other thing that can happen, besides forming this molecular ion, the high energy electron can hit the molecule and it can break a bond. It doesn't have to be a specific bond, it could be one of several bonds. And then what happens is the molecule breaks into two pieces, and one of those pieces will have a positive charge on it. This is called a fragmentation ion. I could have formed this ion, or alternatively, I could have formed this ion. The molecule can break in lots of different places, so you can get lots of different fragmentation ions formed. Okay. So what? Well, here's our ethanol molecule. The mass spectrum is going to give us some kind of graphical readout. Let's introduce you to this axis, the MZ axis. M is the mass. Z is charge. So on our x-axis, we are reading the mass of the thing being detected divided by its charge. Now at A level, the great news is we are only ever going to be dealing with things that have a +1 charge. So effectively, because the Z is always going to be 1, this axis is telling us the mass of the thing, the ion, which is being detected. Now we've talked about the idea that when we bombard our sample with high energy electrons, we can knock an electron off the molecule. So in this case, if I did that, I would form this ion, which I'm going to call the molecular ion, because it's the ion of the molecule. And the molecule and the molecular ion will have the same mass. So I would expect to see a peak somewhere on that axis that corresponds to the molecular ion peak. And that molecular ion peak is telling me the MR of the molecule. That's really important. Sometimes you might see a really tiny peak at one value higher than the molecular ion peak. That occurs because sometimes in a very small percentage of molecules, one of the carbons will be an isotope. It will be a carbon-13 atom, which will mean that in a very, very small percentage of molecules, hence the very, very small peak, there will be a molecular ion caused by the molecule with a carbon-13 atom in it. This axis, the y-axis, is the relative abundance axis. It is telling us the relative proportions of the different types of ions. So, here we've got the molecular ion peak, and it's possible to get an exceptionally small peak at one value just above the molecular ion peak, caused by isotopic variations in carbon atoms. It's not something we need to worry about too much. The key thing here is, can we use a mass spectrum to work out the MR, the molecular mass of the molecule? We're looking for the molecular ion peak. That's the molecule that's had one electron knocked off. And because the mass of an electron is negligible, the mass of the molecule and the mass of the molecular ion are the same. Now, we talked about the idea of fragmentation ions. A fragmentation ion occurs when we break bonds inside the molecule. So let's go back a step to our original molecule. Let's imagine I'd broken that carbon-oxygen bond and I'd created this fragmentation ion. What would the mass of this ion be? And where would I expect to see it along this axis? Well, clearly, I've got two carbons. Each carbon has a mass of 12 and 5 hydrogens. So this is going to have an MZ value of 29. I had a value of 46 for the entire molecule, 2 carbons, an oxygen, and 6 hydrogens has a mass of 46. I'm also going to get a peak at 29. Do you know what? It might even be higher. Who knows? I could alternatively have formed this molecule, this fragmentation ion, the OH plus fragmentation ion. That would have a peak at 17. So what we've got to be able to do at A level is identify the molecular ion from the molecular ion peak and then use that to work out the MR of the molecule, but also use fragmentation ion peaks to work out bits of molecules that could be present. So typically you're going to be looking for CH3 groups, C2H5 groups, possibly CH2OH groups, just parts of a molecule that correspond to particular peaks or fragmentation ion peaks in the molecule. So, if you have a spectrum that looks something like this, I can clearly see, looking at this spectrum, this is the one for ethanol. I have got a peak here at 46. It's not the biggest peak. The molecular ion peak does not have to be the tallest peak, but it is the peak which is the furthest up, which has the greatest MZ value, with the exception of the tiny, tiny peak which may be present at 1 unit higher in value. Now you'll notice, those keen-eyed students, that on this axis, the relative abundance axis is 100%. One of these is 100%. All of these add up to more than 100%. In organic chemistry, mass spectra work in a slightly different way to the work that you've been taught in inorganic chemistry. One of the peaks is always given the value of 100% and everything else is measured relative to that value. So this is the one which has the greatest amount. It's given 100% and everything else is relative to that. So I can use this to identify the MR from the molecular ion peak. That's at MZ46. At 47, that's caused by isotopic variation, the presence of a carbon-13 atom in the molecule. I imagine at 45, well, if you think about an ethanol molecule that's been bombarded with a high-energy electron, and we've knocked off one hydrogen atom. We've broken either the oxygen-hydrogen bond or a carbon-hydrogen bond. A hydrogen's come off, and we're left with a fragmentation ion. Just like the molecule, but one hydrogen less, that's going to have an MZ value of 45. What could be at 29? And what could be at 31? Pause the video, have a think. Okay, so if I think about my ethanol molecule and I start to break it apart into different pieces, if I think about this part of the molecule, if I imagined that I had broken the molecule there, broken the carbon-oxygen bond, and this part ended up with the positive charge on it, 2 carbons, 24, 25, 26, 27, 28, 29, the C2H5, or to draw it out, this could be the fragmentation ion which caused the peak at the MZ value of 29. At 31, well, how else could I break up my ethanol molecule to give a value of 31? Well, I'm going to start from the other end of the molecule. 16, 17. Add 12, 29, 30, 31. So I could think about that part of my ethanol molecule having positive charge. So I would have broken the molecule between the 2 carbons. So this is a fragmentation ion which has an MZ of 31. So all I'm doing is looking at my molecule and trying to identify parts of the molecule that correspond to the same masses that appear on the M to Z axis. I don't need to identify all of them. In an exam question, you'll be asked to identify specific fragmentation ion peaks. Come up with structures that would correspond to those values. Effectively, that's it for mass spectrum. You're using it to identify the molecular ion peak and hence the MR of the molecule, but you're also having a look at fragmentation ions and using them to decide, is there a part of the molecule that corresponds to that particular peak? So here's the worked example. We've got something with an empirical formula C2H4O. The questions are, what's the relative molecular mass of the compound A? What's the molecular formula of compound A? And could we suggest structures for ions that give rise to the peak at MZ15? So is there a fragmentation ion that we could come up with that would have an MZ value of 15? So what you need to do is pause the video, have a go at answering those questions. Okay, what do we do? I can see up here at MZ equals 88, there is a peak. There's a really, really, really tiny one at 89. That's going to be caused by isotopic variation. That's going to be caused by a molecule with a carbon-13 atom. So I'm going to ignore that. I'm interested in the 88. This is caused by the molecular ion. It's called the molecular ion peak. And the molecular ion peak tells us that the MR of the molecule, in this case, is 88, because that's where the MZ value lies. So now I know the MR of the molecule. I've been given the empirical formula of the molecule. Now C2, H4O, when you work out what that all adds up to, the mass of the empirical formula is 44. The MR of the molecule is 88. So there are 2 lots of that present in the molecule. So the molecular formula of the compound is going to be C4H8O2. Now, if I was really, really good at interpreting fragmentation ions, I'd be able to find out lots and lots of things about this molecule. All I'm being asked to do is, can I identify an ion that has a mass of 15? Well, typically, a carbon with 3 hydrogens attached, if that's present in a molecule, when the high energy electron hits that molecule, bonds can be broken, leaving this fragmentation ion behind. That's got a peak at MZ 15.